Let us look now at another alternation of instructions for the bounded buffer problem. Sorry, I just need to put this back in. Yes, sorry. So again, we are starting from the very beginning where empty starts at 1. So max is initialized to 1, full is 0. But now we will start with the producer running first. The first time we started with the consumer waking up first. The producer basically calls wait and on empty. And since empty has the value of 1, so it decrements the 1 to 0. It puts the element that is going to put in the buffer. It calls post. Okay, so now full has 1, so it calls post on full. So full gets incremented by 1, and full now has the value of 1. And then it calls wait on empty again. Since empty is equal to 0, then it decrements it by 1, so it gets to -1. Now the producer has to sleep because -1 is less than 0, and the consumer starts. The consumer basically starts by checking if temp is not equal to -1. The last value basically that was put in by the producer. It calls wait on full. So now full will get decremented by 1, and full will have a 0 in it. It calls get, okay, on and now once it gets the data, it calls post on empty. So empty now will have the value of 0, and then it prints whatever value it got. Now now if basically it goes back to the producer returns from wait, puts an element, posts something into full, so it will work for basically this way forever. So let us ask a question. What if max is done? Will this code, with the put and get codes that we first looked at, work? Actually not, because the put and get code snippets that we were looking at, where you had the modulus of the modulus over the fill and the modulus over the use variables, that code can cause a race condition. Okay, basically imagine that we have more than one producer and P0 adds a value to the buffer, and then there's a context switch to P1 before P0 increments fill, because fill is not protected here. Or imagine that you basically have the buffer overflowing. Buffer overflow is basically when you fill the buffer and you go to the first element to the buffer and you start filling it in the opposite direction before the data gets consumed. But in this case, because fill is not protected by any protection mechanisms, any synchronization mechanisms, then it gets problematic. So this might be a solution where you add a mutex, you wait on a mutex, basically instead of waiting on full, okay, in the producer. So does this work? No, it will not. Let us look at what would happen. So you have the consumer waiting on the mutex, okay. No one has the mutex, so the consumer can continue, okay. And then you basically wait on full. So now you're waiting for something to be filled, and then the producer comes in, tries to wait on the mutex, but the consumer already has acquired the mutex, has already acquired the lock, which basically means that you have a deadlock because the producer cannot proceed as long as the consumer has the lock, and the consumer does have the lock. So this is a fix, okay, where you actually just swap some lines, and these lines will actually fix your deadlock. And this is very common in synchronization in parallel programming, that just swapping the order of how we call things will highly affect the way that your system behaves. So you have to really know what order your locks are taken in. Okay, so in this case, basically, if you start, you check if it's full. If it's full, Okay, then you have to wait for the producer to produce something. Okay, the producer checks if it's empty, and since it's not full, then it's empty. The producer then can call the mutex. Okay, can basically acquires the lock, puts the data into puts the data into the buffer, um, posts the mutex, basically releasing the lock, and posts to full. Okay, so the consumer which was waiting for on full can now acquire the lock, and now the program can progress.